question says, a chemistry graduate student is given 250 milliliters of 0.2 molar acetic acid solution. Acetic acid is a weak acid with a Ka of 1.8 times 10 to the minus 5. What mass of potassium acetate, KCH3CO2, should the student dissolve in the acetic acid solution to turn it into a buffer with a pH of 4.79? Now there are many ways to approach this problem, but first I want to start with the balanced chemical equation. So we have acetic acid, HCH3CO2 aqueous, plus water, liquid, and acetic acid is going to act as an acid. It's the acid found in vinegar, and you're going to get H3O plus aqueous plus CH3CO2 minus aqueous. So like in other buffers, the acetic acid is this one, and the ion, the 1A, often a 1A metal ion, with this negative ion is this one. So essentially we want to find the amount of this we need to add to make the buffer. If you recall, a buffer contains a weak acid and its conjugate base. So in order to do that, there are lots of ways to do this, as I said before, but one way to do it is use the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is pH equals pKa plus log of the concentration of A minus over the concentration of HA. Now, when we're doing this equation, our variable is essentially going to be the concentration of A minus, which specifically for this acid, we could rewrite this as pH equals pKa plus log concentration of CH3CO2 minus over concentration of HCH3CO2, like so. So this is essentially our variable. However, it's a little easier, in my opinion, to solve for this whole thing, this whole log, by getting rid of the pKa and the pH, and then taking the inverse log and solving it for this individual variable, because it's inside the log, and that's just what I think is easier. You could plug it in instantly, it's the same thing. So, how do we do this? Well, we're given the pH of our target, and the goal is to find the concentration of the acetate ion. With the concentration, the volume, and the molar mass, we can find the grams, because it ultimately asks us for what mass should be added. So what we're going to do is plug in the pH, which is 4.79. We're going to plug in the pKa by taking the negative log of the Ka, as we've done in several other videos. So here we take the negative log of the Ka and we get 4.7447. And the sig figs don't work out exactly. It just says to round your answer to 2 significant figures. In this particular one, since when you subtract these, it's a very small number, it may only be 1 sig fig, but that doesn't really matter. So now we have the pKa, which came from taking the negative log of the Ka, as has been done in several other videos, plus log of concentration CH3CO2 minus concentration HCH3CO2. Note that I'm not plugging anything in here yet. Now I'm going to subtract 4.7447, subtract 4.7447, and I'm going to get that 0, I'm going to move this up a little bit, 0.0453 equals the log of concentration CH3CO2 minus over the concentration of HCH3CO2, like so. Now I need to get rid of this log. So I want to take 10 to the power both here, or take the inverse log of both of these in order to get rid of that log. And when I do that, I get that 1.1099 equals concentration of CH3CO2 minus over, I'm now also going to plug in for this, because I'm given this, the concentration of acetic acid, way back up in the question, is 0.2 molar. So I'm going to go ahead and plug in the 0.2 molar. I'm now going to cross multiply, and when I do that, I get that the concentration of CH3CO2 minus equals 0.2 times the 1.1099, and what I end up with is the concentration of this acetate ion is 0.2219 molar. Well, this is also the concentration of K, CH3CO2 minus, that we must add, because every K, CH3CO2 minus, or potassium acetate, that we add will give us one of these. So these concentrations have to be the same. Well, now that we know the concentration of potassium acetate, and we know that we want to make 250 milliliters of solution, we can go ahead and just do basically a dimensional analysis problem. So starting with 0.250 liters of solution times, we know the molarity of the solution we want to make. So for every 1 liter of solution, there are 0.2219 moles of KCH3CO2, potassium acetate. That shouldn't have a minus charge there. We made a mistake there. Times, now we have moles of potassium acetate. We want grams of potassium acetate, so we put 1 mole of KCH3CO2 on the bottom. And on top, we put the molar mass, which happens to be 98.14 grams of KCH3CO2. So basically a solution stoichiometry problem. And when we do that, we find that we need to 2 sig figs 5.4 grams of KCH3CO2. So to quickly review, we use the Henderson-Hasselbalch equation to find the log of the base over the acid. We then got rid of the log, plugged in the concentration of the acid, found the concentration of the conjugate base, and then in turn the concentration of the potassium salt of the conjugate base. Use that concentration and solution stoichiometry to go from a volume of solution given in the problem, the molarity to go to moles, and then the molar mass to go to grams.